We're going to look at how we represent elements using the idea of subatomic particles. And as we look through, we actually use the symbol A over Z with the symbol X. Okay, so as you can see from this, the top number, which is A, is the mass number, protons plus neutrons. Bottom number, which is represented as Z, is the atomic number. That's the number of protons or electrons if it's neutral. And then X is the symbol of the element. Okay, so we have mass number over atomic number with the symbol. Now, a way to remember if you forget is the bigger number should always be on top. Your mass number should always be bigger than your atomic number, with the exception of an electron because that's negative. So all atoms of the same element have the same number of protons, which is the atomic number. So the atomic number is the number of protons in an atom. If it's the same element, it has to have the same number of protons. So all nitrogen atoms have to have 7 protons. If it has 8, it's no longer nitrogen. If it has 6, it's no longer nitrogen. Okay? So if it's the same element, it has to have the same number of protons. And then the mass of an atom is protons plus neutrons. Okay, the mass of an atom is usually given in atomic mass units, which is AMU. The mass number is the sum of protons plus neutrons. Mass number should be a whole number. If it's a different mass number, that doesn't mean it's a different element. That just means that we then have what's called an isotope. So isotopes are atoms of the same element with different masses. So same element means same Z, which is atomic number. If it's the same element, it has the same number of protons, but it has different masses. The whole premise of an isotope is that they have different numbers of neutrons, which means different masses. You can see here an example is carbon. You can have carbon 11, carbon 12, carbon 13, or carbon 14. They all have the same number of protons and electrons because they're neutral, but the difference comes with neutrons. So now I want you to pause the video and try these two examples, these two practice problems, identifying protons, neutrons, and electrons. So pause the video, try this, and then come back and check your answers. So looking at the first example, you have barium-138. The first thing I did was put the atomic number on the bottom. Right, so you have 138 over 56, Ba. Now we want to know protons, neutrons, and electrons. Protons, same as the atomic number. So we have 56 protons, and this is not charged. Right? There's no charge up here, which means it's neutral, which means electrons is also 56. Now neutrons, we have to find the difference between the mass, which is 138, and the atomic number, which is 56. So what we need to do is take 138 minus 56, and that gets us 82 neutrons. So again, we can take mass minus protons to get us our number of neutrons. So in the second example, it tells us magnesium has 3 isotopes. We have a mass of 24, 25, and 26. We first need to write the symbol for each. So we know that it's going to be Mg, and I included the way that we write isotopes, or the way that we write symbols, A over Z with the symbol X. So I know magnesium is Mg. If it's magnesium, it always needs to have the same atomic number. Magnesium's atomic number, if you look on your periodic table, is 12. The only difference is the mass number, which they give us in the problem. Okay, so again, if it's magnesium, it has to have this same number down here. Okay, if these bottom numbers change, it's no longer magnesium, which then means our neutrons is what changes in this bottom problem. Okay, so with this first one, we have 12 neutrons, 24 minus 12. This second one, it's 13, 25 minus 12. And in this last one, it's 14. Okay, so this is how we work with isotopes and with writing symbols. So the whole premise of using isotopes is for us to calculate the average atomic mass. In the real world, we use large amounts of atoms and molecules. We don't use just one. We don't just say, I just need one carbon-12 isotope. No, we use a very large amount. So what we have to use are the average atomic masses. The average atomic mass is what is actually on your periodic table. Notice on your periodic table, they're not whole numbers. Right? If you look at hydrogen, 1.008, that's not a whole number. The average atomic mass is what we use, and we calculate it from the isotopes weighted by their abundances. And so the way that we calculate this, so average atomic mass equals the sum of the isotope mass, so let's say it's isotope 1, times its fractional abundance. Okay, so we take the sum of all the masses times their fractional abundances. What that means is, if you have 4 isotopes, you take the mass of isotope 1 times the abundance, plus mass 2 times abundance, plus mass 3, so on. The big thing here is that this says fractional abundance. So if it gives you percent, put it in a fraction first, right? Make it into a decimal. So we're going to look at an example. This says use the following data to calculate the atomic mass for the element magnesium. So we have the isotope symbol, right? Mg24, Mg25, Mg26. We have the atomic mass, and we have the abundance. So what we have to do is take each one of these, multiply it by the fractional abundance. So I will take 23.982628 times 0.786. Okay, add that, so on. So add them up, multiply it out, add them all together, and see what you get. So after you multiply everything out, add it up, you get 24.30515. Now, we've already looked at significant figures. You have to start using significant figures correctly. It's no longer going to be just, go out to 3 sig figs, you should be fine. Although typically that works, you have to pay attention. If you don't get the significant figures correct, then you won't get the full points. So if we take a look at this, we have in each of our atomic masses 1, 2, 3, 4, 5, 6, 7, 8 significant figures in each of these. So each of these has 8 sig figs. In this percent abundance, count them up, you have 5. In these next 2 abundances, we only have 4. So our answer needs to be rounded to the least number of significant figures, which would be 4. So we'd have 24.30, but take a look, this 5 rounds this 0 up. Our actual answer should be 24.31 AMU. So that's our answer rounded to the correct number of significant figures. Now I want you to try this example on your own. Okay, naturally occurring chlorine is 75.78% chlorine 35, which has an atomic mass 34.969, and 24.22% chlorine 37, which has an atomic mass of 36.966 AMU. Calculate the average atomic mass of chlorine. So try this on your own, pause the video, and then come back and check your answer. Okay, so here you have the problem worked out for this example. You can see that you get 35.45267, so on, but the least number of significant figures in this is 4, so you have to round it to 35.45 AMU. As we discuss isotopes and average atomic mass, we have to talk about using the mass spectrometer. Atomic masses and molecular masses are measured with very great accuracy using this device. A mass spectrometer is a very complex device for measuring masses. You can see a very detailed explanation on page 52 of your book, and I've also posted a video onto the class website under the resource videos for a more simple explanation of how a mass spectrometer works. But in general, the mass spectrometer is used to measure the different masses of each of the different isotopes, and it's also used to determine the number of isotopes and their percent abundance in a specific sample. Before we look at the mass spectrum of different elements, we're first going to talk about how a mass spectrometer works. Again, the link at the bottom is the YouTube link to the video that I've posted under the resource videos, but atoms that go into the mass spec are organized based on the outcome of this process. So in a mass spectrometer, atoms or molecules are passed into a beam of high-speed electrons. And this knocks electrons off of the atom and turns them into cations. So you put the sample in, it knocks off electrons and turns it into a cation. An electric field from these magnets are then applied to the sample, and this accelerates the cations because they are repelled from the positive side and they're attracted to the negative side, and this then changes the path of the electrons. The amount of deflection is proportional to the mass. So the heavier the cation, the less it deflects. Right? The harder it is to move, the larger it is. But then the ions hit a detector, and this is how the measurements are made. So again, you put the sample in, electrons are knocked off, and then you have the positive ions going through the magnetic field, and then they're separated based on the mass differences. So when the atoms go into the mass spectrometer, and you look at the results, which are how they're detected, they're organized by mass, and your relative amounts can be measured. Now, when your relative amounts are measured, that is measured as relative abundance, which is the y-axis. And then the x-axis is actually mass to charge ratio. Now, this is where it gets very complicated, but the mass ratio is just mass over charge. Since we're going to assume that only one electron is knocked off, it is the same as atomic mass. So instead of this m to z, you can just write atomic mass on the x-axis. So it's abundance versus atomic mass. As we look at this mass spectrum, okay, which is essentially the data given off, we can see the isotopic combinations. Okay, so if we look at this, we can see that we have some isotopes with a mass of 92, 94, 95, 96, 97, 98, and 100. What the mass spectrum allows us to do is actually estimate the atomic mass of an element from these results. So we can look and see the mass spectrum for boron. We see relative abundance as the Y, and then we have M to Z as the X. Again, we can cross this off and change this to atomic mass, which is in AMU. This scale of relative abundance is usually made by setting the tallest line to 100. So we can say it's 100% abundant, and then we can read the other lines accordingly. All we really care about is the ratio. If we have 123 atoms, 23 would be boron 10, again, just by reading the graph, and 100 of them would be boron 11. This will allow us to look at average atomic mass. Think about what this means regarding the average atomic mass. Okay, 100 atoms are boron 11. Only 23 are boron 10. What do you think the mass would be closest to, 10 or 11? Hopefully you think, well, look, 100 atoms are boron 11, only 23 are boron 10. The mass should be closer to 11, which it's true. The mass of boron is about 10.8. And so from the mass spectrum data, we can either find the percent abundance and proceed as we did in our last examples with average atomic mass, or we can just use the ratios as they are, and we can do 23 divided by 123 times 10, okay, which gets us 1.8699. Add it to 100 divided by 123 times 11, 8.9431. Okay, and then what we find is the mass. So we can actually add those up, and we get 10.81 AMU. Right, so that's a way that we can actually use the mass spec data to come up with the average atomic mass. Now, again, this is still fairly new in terms of learning it in the high school setting. However, you use this very, very often, whether you're going into forensics. Okay, this can be used to determine different isotopes in a specific sample, whether you're going into chemistry, where you can just use it to look at isotopes in general, or even in medicine, you can actually determine what all different elements based on masses are in a specific drug. And so this is used very commonly when you want to determine what is in a specific sample. So this has a lot of real-world uses, and so it's important that you understand how to use a mass spectrum chart or a graph or how it works in general.